Okay, I'm going to get started. I'm going to do a little bit of a review, so I think even people who come in late won't really be lost. Starting point is, for this review, I just want to remind you, I wrote down a rather pretty and general expression for gravitational wave perturbations as a sum over polarizations A, an integral over frequencies f, that's minus infinity to infinity, an integral over a 2 spheres worth of directions, that's the integral d omega. There's a complex amplitude that depends upon polarization, frequency, and direction. Then there's an exponential e to the I 2 pi f t minus omega hat dot x. And finally, there's a polarization tensor EA, oh, I better put the A upstairs, which depends on the direction that the waves are going in on omega hat. And my notation for omega may look a little bit inconsistent here, but at least in my own head, I've got a clear idea of what I mean. For example, by d omega here, I mean sine theta, d theta, d phi. By omega hat, I mean a unit vector that depends upon theta and phi. So if you want, you could think of omega as being this pair, theta and phi. And I also wrote a complex form of this. I think I'm going to write that as well, just as part of this review here. It looks almost exactly the same, except instead of summing over polarizations, we take the real part. We have the same integral over frequency, same integral over directions. This amplitude is now complex, but it doesn't have the property that if you change the sign of f, it complex conjugates. That's why it has more information in it. And then there's still the exponential here, I 2 pi f t minus omega hat dot x. And finally, we have a complex polarization tensor here. If I had picked my m's and n's to point the right way, this would be a right-handed, but I honestly can't remember if I did it correctly or not, so it might be left-handed. Anyway, it's one of the two-handednesses. You want the other one, you take the complex conjugate. And E plus and E cross were sort of standard linear polarizations, and E in terms of those was E plus plus I E cross. And implicit in all of this is that these polarization vectors depend upon the direction of propagation. And you remember the way I defined them is I defined a triad of right-handed vectors. We had omega, this unit vector, which was a function of theta and phi, and then we also had an m hat and an n hat. All of these you should think of as functions of omega. This is a bit of a tautology that omega hat depends upon omega, but if you want, you can think of this as being the sums of the x, y, and z components, cosine phi, sine theta, x hat, and so on, which depend upon theta and phi, but it's actually a vector. Okay. Any questions or concerns about that? All right. And just like, you know, warming up before you do sports or something, let's do a couple of very quick little thought exercises here just to get you thinking along the same lines as me. Well, for example, suppose I consider this combination. I take the vector omega hat plus m hat plus n hat. Oops, that should be a B. And that should be a B as well. Okay. Look at that combination. So, you know, for a particular direction of the wave, that might be x hat plus y hat plus z hat, for example. Okay, graduate students only. Postdocs, faculty, whatever, can't answer these questions. Neither can the people who were sitting with me at dinner last night. I think I showed them this. But is there a simple way to write this expression? I mean, I could write it in terms of thetas and phis, right? I could write each of these vectors in terms of theta and phis, and I could write out some big mess there. I'll give you a hint. Suppose I took the dot product of this thing just on one of the indices with some vector v, like that. So I contracted. So this would give me the component of v pointing in the direction of omega hat times omega hat. Yeah? Uh-huh, it is. It's the identity, right? I take any vector, and this projects out, you know, the part pointing along omega, and then I multiply by omega, and I get it back, right? So in fact, that's what I was looking for. This is just delta AB, you know, the identity matrix or the identity operator, for example. Is that clear?
Sorry, I just have a question about indices.
Yeah.
Space-time
Good question. So remember, this is transverse traceless synchronous gauge. Synchronous means there's no time components. So A and B here, I mean, if A and B are time, 0, okay, the value is 0 because these quantities are purely spatial. So A and B are 1, 2, 3, X, Y, Z, and I'm being very sloppy about upstairs and downstairs because it doesn't matter. Okay. Any other questions? So, okay, let's keep going here, just warm-up exercise. Suppose I do this. Suppose I integrate d omega. I'm going to divide by 4 pi here, by the way. That means that if I integrate 1, integral d omega over 4 pi, I'll get back 1. It's kind of like an averaging. What about this? Suppose I integrate omega hat, d omega. What do I get? How come? Symmetry, right? Every time there's a vector pointing that way, there's another one pointing the other way, which has the same weight. So that's 0. Also true for m hat and n hat, right? By the way, spending some time playing around with these polarization vectors, you know, a day or two, is a really good idea because they actually appear in a lot of other contexts. For example, if you're doing CMB analysis and you're projecting the electric and magnetic fields onto the celestial sphere, you know, the components transverse to your line of sight are described by similar sets of vectors. So these things occur in other contexts as well, not just gravitational waves. Okay, what about this? Suppose I do the integral d omega over 4 pi, but this time omega hat A, omega hat B. Now the symmetry argument doesn't work, right? Because the vector pointing that way doesn't cancel the one pointing that way. Any thoughts? It has to be proportional to the Kronecker delta. Mathematically speaking, this integral is invariant under the rotation group. And this is a rank 2 symmetric tensor, and the only rank 2 symmetric tensors that are invariant under the rotation group are proportional to the identity. So that's the technical reason, but you know, Feynman would just say this is obvious by symmetry. It's got to be proportional to delta AB. What's the constant of proportionality? How do I get that? Contract. On the left-hand side, this dot product gives me 1, and I get the integral of d omega over 4 pi, which is 1. On the right-hand side, if I contract that, I get 3. So right answer is that. I could put an m hat in here, and I'd get the same thing. Same result. Also n hat, right? What if I had 3 of them? Yeah.
Sorry, for the previous one, you wrote omega equal 0, and you said if it was n or m would be the same.
Yes.
But one of them has a z component that is minus sine theta times z,
Mm-hmm.
and this doesn't average to 0. The n one would give something that we can see later.
That's true. Huh. Well, you've messed up my logic. All right. It's true for omega, it's true for m. Huh. I'm going to assign this as an exercise. I hope you agree with at least these two equations. And similarly for n hat, n hat. I won't actually need these. They were meant to be a warm-up exercise, but I guess I'm the one who's going to have to do the warming up here. All right. I want to assign something. This is a problem, which is the following. Work out what if the following integral is. It's d omega over 4 pi EAB E star CD. And of course, you can do this by writing down all the variables and doing it, right? But it's quite a mess because there's a lot of different powers of sine and cosine that enter into that. Whereas you can do it purely by symmetry arguments. And the hint here is that there's a couple of different things you can form that have the right index symmetries and properties, and then by taking various traces, you can get the right result. Okay. All right, so much for warm-up. It's going to be tough for me to concentrate now. I've got to figure out what's wrong with my argument. Okay, so I want to do another just simple case here. Now, I told you before, you can think about this quantity as the amplitude associated with the wave at frequency f going in direction omega. Let's do just a simple case. Let's suppose, for example, that HA of f and omega is just some function of frequency. I'll call it capital H of f. And then there's a two-dimensional delta function of omega and omega 0. So what I mean by that two-dimensional delta function is just, well, I could write it in a couple different ways. I could write it like this. It's the sum over L and M of spherical harmonics of omega times their complex conjugates in terms of omega prime. That's kind of one nice way of doing it. I could be a bit more pedestrian and just say delta 2 of theta phi. That's the coordinates of omega, theta prime, phi prime. That's a delta function of theta minus theta prime. That's an ordinary Dirac delta function of phi minus phi prime. And then I need something that cancels the sine theta in the measure there. So I guess that better be sine theta down there. So suppose we do that. So now you can do this integral immediately. Oh, I want to put an index on my h here. I want to allow myself to have two different functions, capital H. So there's a frequency-dependent thing here, and what I've done is I've just said, okay, this function is now going to be 0 except for a particular gravitational wave propagation direction. That's the case, by the way, where you have a source located infinitely far away. If you have a source near me, in fact, this function h wouldn't vanish if omega was different than that source direction, because if it's nearby me, the waves actually have spherical wave fronts, not planar. So this case really does correspond to a point source, but not just a point source, but a point source that's extremely far away, so that you get plane waves and not spherical waves. So we can immediately just evaluate the integral. Let's do that. So we get HAB of t and x is an integral df. There's an h plus of f e plus av in the direction omega 0 e to the 2 pi I f. I'm going to just erase this. Two pi I f t minus omega 0 dot x. And I'm just going to write plus the corresponding h cross term. Now, if you think about, I think I'll do one other thing too here. I'm going to put a bit more consistent with what Teja was doing yesterday. I'm going to put a twiddle over the h's here. So if you think about this, you'll just recognize that this is just a Fourier transform of h tilde of f. And this, by the way, is the reason why we need both positive and negative frequencies. If I write the Fourier transform of h tilde as, let's say, h plus of t is the integral df e to the 2 pi I f t h tilde plus of f. So in other words, if this function here of frequency, its Fourier transform is just some function of time, then you can see what form the metric perturbations take here. They just become HAB of t and x are whatever this function h plus is, it's a function of a single variable, but the argument is t minus omega 0 hat dot x. Then there's the polarization tensor E plus, AB of omega 0. And then there's the corresponding term, which I think I'm not going to write down. I'll just write down plus H cross E cross. So that's a plane gravitational wave. It has wave fronts that are constant on surfaces where t minus omega 0 dot x is constant. So source infinitely far away, these are just wave fronts that are arriving. And this function h plus and this function h cross are totally arbitrary. You can make them whatever you want just by picking these Fourier transforms here to be whatever you like. And by the way, there's lots of obvious properties of this. For example, it's obvious that this solves the wave equation, right? If I take minus d squared by dt squared plus d squared by dx squared, plus grad squared. If I apply this operator to that, you can see what happens. For example, the time derivatives just take two derivatives of this function h with respect to its argument t. So you can imagine putting 2 primes on this and 2 primes on that for the time derivative. That's easy. And the gradient with respect to x. Well, the first time you take the gradient, the chain rule says you take one derivative of this h, and then you bring down a minus omega 0 hat. Second time, you take a second derivative, you bring down another omega 0 hat. That dots together with the first one. And so the wave equation is satisfied. So this is actually the same solution that Matthias wrote down in the very first lecture of this school, except that he just had picked the gravitational wave propagation direction to be z. So this is just the same thing, but going in an arbitrary direction. Okay. Good. All right, so next thing I want to switch to now is what I was starting on the last lecture, which is to talk about the effects of this gravitational wave now on the propagation of light. So this is how detectors work. And the picture I've got here is there's a pulsar located at x equals L, and there's, for example, a radio receiver on the Earth. And pulses of light are traveling from the pulsar to Earth along null paths. And this problem was studied by Sachs and Wolf in 1967, and they wrote down a formula, and I'm just going to write it down again. And I'm going to write it in the following form. They wrote a formula for the time delay. I'm going to write it delta t. It depends upon the arrival time of the pulse. And actually, I think I'm not going to write a formula for that. I'm just going to say arrival time delay. And the idea was that in the absence of a gravitational wave, that's 0. Whereas in the presence of a gravitational wave, this quantity depends upon the metric perturbation along this path. And basically, you integrate the time derivative of the metric perturbation along this path to figure out what that time delay would be. And the calculation's non-trivial because you have to actually ask about how does the path get distorted by the gravitational wave. And so the answer is simple, but there's a few steps along the way. And it turns out this quantity is not so convenient to talk about. What is very convenient to talk about is instead the redshift, which is the time derivative of this. And let me just say a bit about that. So first of all, the word redshift. These pulsars are clocks. They're ticking, for example, 100 times a second. And as the light propagates to us, or as the radiation propagates to us, for example, if these pulses are delayed with respect to one another, so the arrival time between them is longer than it would otherwise be, that corresponds to the clock slowing down. So if that clock were a laser and it was red, it would be slightly more red. It would be a lower frequency. So because of the principle of equivalence, all clocks behave the same. The biological processes in your body as clocks, they behave the same way as oscillators or anything else. It's the reason why, if you've seen the movie Interstellar, the people who are on this gargantuan black hole, they go through 2 hours of time while the person orbiting up above goes through a number of years. And the point is the clocks that they're looking at on their wrists or the oscillators that they look at, they behave the same way. And if they looked, for example, at the clocks ticking for the people they left behind, if they looked at that, they'd see those ticking very quickly. So the word red shift and blue shift here, if I'm looking at these pulses and they're coming 100 times a second, there's no red or blue associated with them. But the shifting of frequency, of the fractional frequency, is described in the same way. So I'm using the symbol Z here for redshift, even though there's no color involved in this particular clock. And so the idea is that, for example, if these pulses are coming farther and farther apart from each other, if this time delay here is a linearly increasing function of tau, then this derivative is constant, and that corresponds to a constant positive redshift. So positive redshift means frequencies are going down, and that means that the pulses are arriving further apart. Okay. And now the Saxon-Wolf formula is that this is 1/2 PAPB. So this is a unit vector pointing from us to the pulsar in this case. And then there's an integral, ds, from 0 to L, I'll write down the path again, of the time derivative of h, and that's the derivative with respect to the first argument, of t along the path and x along the path. And t along the path, well, I want t to increase, so s equals 0 is when the pulse leaves the pulsar, L is when it arrives. So I guess that this must be, I want it to increase with increasing s, so this must be, I've got to be careful here. No. Sorry. That is right, pardon me. So it's s minus L plus tau. So when tau is equal to 0, this path starts, it's the one that's shown sort of in the bottom there. This path starts at t equals minus L down here, and then advances up to x equals 0. And then x is just L minus s times p hat. So when s is equal to 0, we start at L times p hat, and then as s increases to L, we end up at the origin. So those equations in that picture are a complete description of how the gravitational waves affect the arrival time of pulses. And let's just evaluate this. I'm going to do it for the plane wave that I wrote here. And then we're going to do it also for the somewhat more general form up there and talk about that. So z of tau. Let's use this form. And let's stick in those equations. And this will be a challenge because I can't see what I've got written down over there, but I'll do my best. So first of all, we're going to have 1/2 PAPB. I'll do the plus one first. There's going to be an E plus AB of omega 0. And then there's going to be an integral ds from 0 to L of H plus. And now what's the argument going to be? So the argument here is t, so that's s minus L plus tau. And then minus omega 0 hat dot x hat, dot x rather. And x is L minus SB hat. And I forgot something. What did I forget? Comparing the equations? Thank you. I forgot to take the time derivative, right? There's an h dot there. So I should have taken the derivative of this with respect to the first argument. So what does that do? That just takes the derivative of h by the chain rule. So I'm going to put a dot over this. And that means derivative with respect to the argument of h plus. Okay. So this integral is pretty easy to do because if you look at it, right, this argument here is just, oh, and then there's, of course, plus the, I'm just going to say plus the cross term, which is identical in form. So this integral is easy to do because I'm just integrating the derivative of something. The only complication here is that the rate at which s is advancing has got a factor here. So if I rewrote this argument, I could rewrite it as s times 1, that's from there, plus omega 0 hat dot p hat, plus the other term, plus the constant term that doesn't depend upon s. So when I integrate this, I'm going to get a factor of 1 over 1 plus omega 0 hat dot p hat coming out. So let me just write down the answer. So we're going to get 1/2 PA hat PB hat. I'm going to stick the E here, E plus AB omega 0, divided by 1 plus omega 0 hat dot p hat. And then I'm going to get h of this whole argument here evaluated between the two ends, s equals 0 and s equals L, plus, of course, the cross term. I hope somebody checks my algebra and tells me that I wrote down the right thing there. Yeah? The time derivative came off because I integrated, right? So differentiate this with respect to s, right? What happens? The argument here, perhaps I should have written it that way. I get an h dot here, but then I also pull out this factor, right, which is multiplying the s, which cancels the one down there. So the dot's not there. Okay. Any other comments about this? Questions? All right. So All right, so now let's evaluate this thing at the two endpoints. So when we put s equals 0, we get a minus L plus tau from here. And then here we get just omega hat 0 dot p. So there's that. And then there's H plus. So at the upper limit here, we put S equals L. That cancels. That cancels. And we just get H plus at time tau. At the lower limit, we get H plus at tau minus L times 1 plus omega 0 hat dot p hat. Hopefully I did that correctly. 0. Looks right to me. Any objections? Somebody got to be checking my algebra here, or I'll get it wrong. Yes, thumbs up, thank you. Okay. All right, so, and then of course there's the other term. I'm just going to write plus the cross term. So identical in form, just replace the E plus here with an E cross and the H pluses with H crosses. Now this is really interesting because if you think about what this H plus is here, together with the E plus, I could write this in another way. A little bit deceptive, but let me try doing that just to make this a little bit more transparent. This is E plus AB of omega 0 times the amplitude, HAB, or dotted into the amplitude at time tau at position 0, right? After all, if I go back to the formula, which I've put in the box up there, and we put t equals tau and x equals 0, so that's at the Earth, or at the solar system barycenter, then you can see that H plus here just becomes, H plus of tau. So this is the gravitational wave amplitude evaluated at the Earth at the time that the pulse arrives. And what about the other term back here? The other term back here is the gravitational wave amplitude at time tau minus L at LP hat. In other words, this is the difference between the gravitational wave amplitude at the Earth at the time that the pulse arrives and the gravitational wave amplitude at the location of the pulsar at the time that the pulse left the pulsar. And of course, then there's the other term, E cross AB of omega, and then there's an identical thing for that. So I'll just write, copy it down. So this is really interesting because it means that what you see here at the Earth, right, depends upon an integral along this path. And because we took a time derivative and then we integrated it, we just end up with boundary terms. There's this nice physical interpretation to this. It was originally given by Detweiler. You have to go to some effort to make this rigorous, but here's the idea. The idea is that the pulsar is a clock, and as the gravitational wave goes by it, effectively it redshifts or blue shifts that clock a little bit. You could think about it as being some motions, like the gravitational wave makes the pulsar move. Now, same thing happens at the Earth, right? The gravitational wave as it passes by the Earth also makes. What's the change in the clock frequency? Well, it's the difference between the velocity that the pulsar got as the gravitational wave passed it when the pulse was emitted, and whatever velocity our telescope has as the Earth moves when the pulse arrives. That's one way of thinking about that difference. I think I have a picture here, which might be also helpful. Think about the following. The pulsar is out there. It's 1,000 years away from us. And there's pulses traveling along. Yeah.
In the second line there,
Yeah.
should the E not be absorbed by the lower T stationary?
You're absolutely right. You're absolutely right. I'm sorry. That is absolutely right. Thank you. I felt that something was wrong in what I'd written. It's simpler than that. Yes. Good. I'm doing a good job of lecturing because you found my mistake. Thank you. All right. In fact, let me try and clean up my mess here. Good. So that's both terms. Is there anything else that I've gotten wrong here? Okay. So anyway, so think about like this path. It's 1,000 years long. The pulsar is, for example, emitting pulses 100 times a second. So over a year, that's something like 10 to the 9 pulses. And so, these pulses are traveling down a path from the pulsar to us. So I guess I was thinking here of 10 to the 3 pulses per second, so a kilohertz clock. And one way of thinking about this is that when the pulses leave the pulsar, the metric perturbation, at the time the pulse leaves, at the location of the pulsar, is modifying a bit the length of the ruler, which is determining how far apart these cars are, or how long each car is. And then, the ruler at the Earth is also modified. And so what you see is the difference. Another important fact here is, because you're integrating along this path, if you have a sinusoidal gravitational wave, right, the integral along the path, each cycle that you integrate over gives you 0. So what you're seeing here is the difference between, the value initially and the final value. Every cycle in between is integrated away. So this is not like a classic ground-based gravitational wave detector where making the arm longer makes you more sensitive. Here, once you've made the thing longer than a wavelength, you're just integrating away the effect. Okay. Let's do the same thing for the general. No, actually, I want to do one more thing with this before we go on. Or do I? No, let's just do the more general case now. Get it out of the way. I said something before. Let me just say why I said it. I said this is deceptive. Here's what's deceptive about this. This formula is not true in general. Because, think about how I derived it. I derived it by assuming that I had a single point source, a single plane wave. This direction, omega hat 0, that appears here, if I put in a general h here, a general metric perturbation, it's not associated with a one direction omega 0 hat, right? Because this function, wherever it is, there, HA of f omega, it has support in general for all directions omega, for many of them. So if you tried to apply this formula not for a single point source, you wouldn't know what value of omega 0 hat to use here. So in some sense, this is a better form than the one below. I wrote down the one below just to get you to think about the fact that one of these things is evaluated at the Earth at the time the pulse arrives, and the other one is evaluated at the pulsar at the time the pulse leaves. And that's sort of implicit in the retarded times here, but that's why I wrote down that second form. Okay, so let's do the same thing but for this general perturbation that I've got written up here at the top. So it's actually very easy, right? Because we're going to do exactly the same thing here. So we're going to substitute in t and x given by the path that I've got over here. And then again, we're going to integrate with respect to s. And so I think I can do that by inspection. So I'm going to get a 1/2 p hat A, p hat B. Then there's going to be the sum over polarizations. There's going to be an integral over frequency. There's going to be an integral over directions. There's still going to be an HA of f and omega. Then there's going to be the effects of integration. So I guess I'll write the EAB here. It's going to be an e to the 2 pi if tau. There's going to be a 1 plus omega hat dot p in the denominator. And then there's going to be the difference when I evaluate the integral between the upper and lower limits. So the upper limit's going to just give me a 1. And the lower limit is going to give me a minus e minus 2 pi I f L (1 plus omega hat dot p hat). There we go. Okay. Anybody want to say they got the same thing? Yes? Good. Okay. So look at where the two terms came from. This term was the Earth term, right? If we just had everything else here, it would be just like analogous. The integral here would be giving me the gravitational wave amplitude at time t at the location of the Earth at x equals 0. That's this first term. That's the Earth term. This other term is the pulsar term. And it's interesting to look at because look what's going on here. For example, if we're looking at frequencies of one oscillation in 10 years, so f is, let's say, 1 over 10 years, and L is 1,000 years, that's the distance to a pulsar, this number up here is like 2 pi times 100. 600. So as we vary the direction of the wave, this is rapidly oscillating. It's like interference. If you get the distance to the pulsar just right, this term cancels that one, right? That's the case where the Earth term and the pulsar term just subtract away. Then shift your wave direction slightly or your pulsar direction slightly, and now instead of destructive interference here, you get constructive interference. And so this this term, it's really very interesting. And I'm going to talk now about how this detector responds and do a couple of cases. Are there questions? A couple of people look confused. And I can't tell if it's because I made a mistake in my algebra or if there's a question. Go ahead.
Just a single pulse. What do you mean by interference?
Think about what's going on here, right? We're integrating. Imagine you have. So this is a plane wave decomposition, right? Each thing that appears in the integral here is like a plane wave of a given frequency. And so what you're doing is you're subtracting the value at one point along this plane wave from another point, right? It's like a sinusoid. And that's what happens when you have interference, right? You add together two things or you subtract them, and they can add constructively or destructively. So this, I'm calling this interference just because this is the sum or the difference of the wave at two different points. Are there other questions? I can't see your hand, just shout out. Yeah.
If this expression is recast in terms of spherical function decomposition instead of plane wave decomposition, does it have any use or any different?
It's actually very pretty, and I'm going to get to that in a later lecture. Okay? In fact, I'll mention that a bit later today since you asked the question. Okay? It's a good question. In fact, I'll mention it in a couple minutes, okay, if I don't, ask me later again. Are there other questions? All right, so let me go on with this. I want to talk now about the response here in a couple of different ways because it's important for what follows. Get some more space. Okay, so let's break this into two parts. First of all, you notice there's this part here, 1/2 PA hat PB hat, dotted into a polarization tensor divided by 1 plus omega dot P. I'm going to call this F. It depends upon the direction the gravitational wave is going in and the direction to the pulsar. It's 1/2 P hat A, P hat B. I'm going to make my life easier here by making this complex. So, you know, I've got a plus term for the plus polarization, a cross term for the cross polarization. I'm just going to combine them both and just say EAB over 1 plus omega hat dot P hat. So that's the prefactor. That's this term, that, and this factor. And so, you know, the real part of this, remember this complex polarization tensor, the real part of this is just the plus part, the imaginary part is just the cross part. So all the information is here. Now when you look at this, you might worry and you might say, look, I'm worried that this omega hat dot P hat here might be -1, right? That's the case if the gravitational wave is going, let's say if the pulsar is that way, and then the gravitational wave is traveling towards us. That's the surfing case. So if the gravitational, if the pulse from the pulsar is surfing on the gravitational wave, then this dot product is -1, and you might wonder that this thing blows up, right? Something looks like it goes wrong, but it doesn't. Let me just prove that it doesn't. And to do that, the easy way to prove that is let's write EAB. Remember that that was E plus I E cross. I had a very nice expression for that yesterday. It's M hat A plus I N hat A times M hat B plus I N hat B. Right? You can tell by inspection. The real part of this is just M hat A, M hat B minus M hat A, N hat B. That's E plus. And the imaginary part is just M hat A, N hat B plus the other term. So it's obvious from inspection that this form is E. So let's look at the complex modulus of F. And let's make our life, let's actually start off by looking at the modulus of the numerator. So let's look at the modulus of P hat A, P hat B, EAB. So this is just the modulus of the complex number that you get by dotting the pulsar direction into the polarization tensor. So that's the modulus of P, I'm going to write it like this, P dot M hat plus I N hat squared. Right? Because when I take the dot product here, I've got two P's dotted into this expression. So, one of the p's dots the first one, the other p dots the second one. And so I just get p dot that combination squared. Okay. But of course, the modulus of the square is the square of the modulus. So this is p hat dotted into m hat plus I n hat times p hat dotted into m hat minus I n hat. There's p dot m plus I n, and there's its complex conjugate. So modulus of the square is the square of the modulus. And I can write that. This is actually kind of handy to use now indices. That's p hat A, p hat B. Okay, there's an m hat dot m hat here. Plus an n hat A, n hat B. Any suggestions on how to simplify that further? Think back to our warm-up exercise. Exactly. But we saw this before, right? Because we already in our warm-up exercise, top left.
Like in the middle, sorry.
I'm glad you can see it. Okay, there, you're right, there it is in the top left. Right? Remember, if I summed omega hat plus n hat plus m hat, that just gave me the identity operator. So what we've got here is PA, PB times delta AB minus omega hat A, omega hat B. But p hat's a unit vector. So p hat dotted into p hat is 1. And the other term here is p hat dotted into omega hat. So it's 1 minus p hat dot omega hat squared. I'm sorry that the writing is getting so small here, but I think I'm going to break my rule of working left to right. I'm going to just keep doing the calculation under here because it's going to be easier to follow. So what was I doing? I was calculating the modulus of the numerator of f. So what does that mean about the modulus of f? Well, it's 1/2 the modulus of the numerator. That was 1 minus p hat dot omega hat. Sorry, it's 1 minus p hat dot omega hat squared. And then in the denominator, there's a 1 plus p hat dot omega hat. But of course, I can rewrite this as 1 plus p hat dot omega hat times 1 minus p hat dot omega hat. I can cancel out the common factors. And so that's just 1/2, 1 minus p hat dot omega hat. So, okay, people shouldn't be looking confused right now. Somebody want to ask me a question about this? If somebody's confused, they should ask. Go ahead.
Is there a 1/3 missing in the delta AB minus omega 3?
No, there's not. Because remember, it was the average value of omega hat dot omega hat that had the 1/3, right? Go up to the very top line here, right? If we add together the 3 perpendicular vectors, that gives us the identity operator, which you can see by just, dotting that into a vector. Good, okay. So this is kind of cool, right? It means that, in fact, although that object, f, looks like it's singular in the surfing case, actually it's quite well behaved. So this quantity here goes between, the dot product here goes between -1 and 1. And that means that this modulus goes between 0 and 1. So f here is in the range from 0 to 1. When is this maximum and when is it minimum? Well, this quantity is maximum when p hat dot omega hat is -1. So that means when the direction to the pulsar is opposite the direction that the wave is traveling. So that's the surfing case, right? That's the case where as the photon travels, or as the pulse travels from the pulsar to us, it's staying always on the same phase of the wave that's traveling with us. But that's very interesting, right? It means that with a place where f is the largest, where this thing is a maximum, this term vanishes, right? Even though let's say the geometrical part of the response, f, is maximum, in fact, there's exact cancellation in that surfing case because the strain at the pulsar at the time the gravitational wave left, or time the pulse left, it just cancels the one at the Earth. So the place where f is maximum, you still get zero response because of that cancellation. So let me make a sketch of what the response looks like. And I've got a better version of this, but I want to get the idea across here before I show you the nicer version. So let's let our pulsar be sort of up here. And this shows the wave direction sort of coming down. So this function, f here, this is maximum. And the pulsar direction goes to 0 in the anti-pulsar direction. So that's sort of the outline of the antenna pattern. It says that this part of the response, the modulus of this factor in the front here, is biggest for a gravitational wave source that's located behind the pulsar. But there is the subtlety, though, that the Earth and pulsar terms cancel for that case. So even though this kind of geometrical factor f is maximum there, there's actually going to be zero response. And of course, if we go to the other direction, so this is the anti-surfing case where the gravitational wave source is behind us and the pulsar is there, then this factor goes to 0. So there's no response in that case. Now, what about this interference term? The difference between the Earth and the pulsar term. Well, what's the effect of that? It's the following.
Sir, I have a question.
Yeah.
So what would happen with the denominator, 1 plus omega half dot p half?
I've incorporated that here. That's part of this factor f. Are you talking about this term? Are you talking about what's here? See, what I've done is I've extracted. I took this factor here, the polarization tensor there, and that factor there. Maybe I'll write this equation down in a slightly different form. Okay, I'll do that in a second, okay? All right, so what's going on here? What's going on is this. If we have a source that's located directly behind the pulsar up here, then even though this function f is maximum, those interference terms, the 1 minus the exponential, give 0, exactly for that case. So we get 0 response in that direction. But if you move very slightly off the axis, if you shift omega hat just a little bit away from p, remember that f times L is big, like a few hundred. You only have to shift a little tiny bit away before that exponential, instead of being +1, becomes -1. So this is what the response looks like. It looks like a series of lobes like that. Similarly, also in the other direction. Okay, I'm as bad at drawing as Barack is, so I'm not going to try and do better. But you get the idea. For the surfing case, you get 0 because the Earth term and the pulsar term cancel. You shift over a small amount in angle, and actually you get the largest response. Shift a little bit more, you get 0, and then the large response, and so on. The number of these lobes here is approximately equal to the frequency of the wave times L. So for example, if it's a 10-year period and the pulsar is 1,000 years away, there's 100 lobes. By the way, that means if we knew the distance to pulsars precisely to better than 1 gravitational wavelength, and we had 60 of them, we've got an amazing phased array antenna. Because each different pulsar would be sensitive to very particular parts in the sky, and if we overlapped all of those different response functions, we have an amazingly precise, pointable antenna. Unfortunately, we don't know the distance to pulsars, or very few of them precisely, so that doesn't work. But it's an intriguing thing to think about. Okay, yeah.
Can I ask a question?
Yeah.
Could you repeat about the axes Earth in this plot?
Yeah, so the idea is this is the response for a gravitational wave coming from that, the gravitational wave is coming from a direction here. So, okay, let me try and be precise here. So the angle theta, so if I want to, I could write this as 1 minus the cosine of theta, where theta was the angle between omega hat and p hat. But remember that omega hat's the direction the gravitational wave is traveling in. So if omega hat is pointing towards me, that means the source is at minus omega hat. So if I want to, I could rewrite f here, not as 1 minus the cosine, but as 1 plus the cosine of an angle, where that angle is the angle between the source direction and the pulsar direction. So in this plot, this angle here, theta, is that angle. So when theta is equal to 0, that means that the pulsar and the source have 0 angle between them. And that's the case where f is maximum. So that's this white circle being largest right here. But the response, because of the cancellation of the Earth and pulsar terms, is exactly 0. So that's the reason why the orange curve goes to 0 there. And then I vary a very small angle theta away, and then that interference term, FL times 1 plus omega hat dot p hat, suddenly becomes I times pi. And then I get constructive instead of destructive interference. It's clear?
Again, the Earth is in the origin of this plot, and we are looking at different.
Right, you can think of the Earth, us being here, and we're looking sort of up at sources. So the pulsar is up here, and then this is the angle to the source. Okay. I've got some better pictures. So this is showing what happens to the antenna pattern as you move the pulsar further and further away. I've forgotten what the exact numbers are, but this is the sort of response that you get if the pulsar is just a couple gravitational wavelengths away. So you just get 1 lobe. And this is when it's a half a dozen wavelengths away, and so you get a few lobes. And this is as it gets still farther away, and you get more lobes. And you can see that I've been sloppy in my drawing because I put these lobes up here a bit too close to the direction. All right. Okay. Question, how am I doing for time? I've got until 12:45. 45. Okay, I got another 10 minutes. Great. Let me say, let me answer the nice question that was asked in the back. I'm not going to talk about it in any detail now, but I will get to this in a later lecture. This function f, sort of the geometrical part of the antenna pattern, by the way, I didn't write it here explicitly, but remember these E plus and E cross are also functions of omega. This has a very beautiful expression, which is the following. It can be written as a sum over spherical harmonics of a set of coefficients that only depend upon L, not upon M, times spherical harmonics that depend only on the direction, of the pulsar. And now here's the fun part. Times spherical harmonics of spin weight 2 that depend only on the gravitational wave direction. And I'll have to double check this, but I'm pretty sure that the ALs are 4 pi minus 1 to the L over L plus 2, L plus 1, L minus 1. I'll have to double check that. I may be missing a square root in the denominator. I put a question mark next to that. This is a really interesting form because it shows that the way that the antenna pattern transforms, it transforms as a scalar under rotation of the pulsar direction, but it transforms as a spin weight 2 tensor under rotation of the gravitational wave direction. And that's exactly because the polarization tensors get carried along that transformation. The way that they transform is with spin weight 2. So this is a rather nice form, but it's a bit out of context right now. I'll come back to that later. I'm going to use that. So let me finish up by just saying a little bit more about how pulsar timing arrays work, and then I'm going to get sort of more deeply into the analysis the next time. And by the way, this is just yet another one of these antenna pattern responses. So here's the factor F. That's the dotted white line, which is slowly varying. And then here's the side lobe pattern, which is the difference between the Earth and pulsar term that oscillates between 0 and 2, roughly speaking. Okay. Of course.
It may be amazing, but why does, like, the longer the distance is, we have more, I don't know what to call it.
You're asking about the density here, the fact that they're not equally spaced. Yeah, it just comes about. You can see why that is, right? The change in phases. So let's imagine that, I don't know, let's say F times L is 100. Okay. So what have we got in the exponential there? We want to know, so each one of those zeros is defined when e to the I 2 pi FL times 1 plus omega hat dot p hat is equal to e to the I, what do I want here? I want e to the I, let me just write it like this. So let's find out where we get constructive interference. So we get constructive interference whenever this exponential is minus 1. Okay, and it's minus 1 whenever the argument to the exponential is let's say, gosh, I am thinking slowly on my feet right now, is pi, some multiple, okay, pi. So whenever this is e to the I pi plus 2 pi n. Does that look right? So whenever this equation is satisfied, the exponential is minus 1. The exponential being minus 1 means that 1 minus that exponential is 2. We get constructive interference. So that's the equation that defines where are the peaks here. Okay. Yeah.
In the solution,
Yeah.
the first spherical harmonic, that's just spin weight 0?
Yep. This is spin weight 0. That's spin weight 2, because the way it transforms as a function of the pulsar position is spin weight 0, but the way it transforms as a function of the gravitational wave direction is spin weight 2. Okay? All right, so there's one last thing I want to do. I better speed up here, but let me just say, can I leave this as an exercise? I'll leave this as an exercise. Go ahead and solve this equation, and what you'll find is that you need uniform steps in the cosine of the angle. Right? It's not that the angle gets uniform steps. This quantity is the cosine of the angle. And it's because the cosine of the angle gets uniform steps that it looks like that. Okay. All right, there's one last thing I want to do. Sorry, I'd forgotten I wanted to do this, but it's actually important. these equations describe gravitational wave detection full stop. All gravitational wave detectors operate on the principle of how do gravitational waves affect rays of light. The lasers in LIGO are clocks, just like a pulsar ticking is a clock. And so these equations apply perfectly well to LIGO as well as to PTAs. And let me just show, though, the interesting thing that happens. You see, in the pulsar timing array, this L times F is hundreds. Whereas in LIGO, the arm length L is 4 kilometers, whereas the wavelength is thousands of kilometers. So a pulsar timing array uses very long arms, much longer than a gravitational wavelength, whereas a ground-based detector has arms that are very short. So just for fun, I'm running out of blackboard space, but let's see if I can squeeze it on the bottom here. Let's look at what happens in the small length limit. So let's take the limit, L times F is much less than 1. But you can do that in your head, because when FL is very small, then the exponential there is just 1 plus the argument. So look what happens. We get z of tau is 1/2 the arm direction. Then there's a sum over polarizations, an integral over frequencies, an integral over directions. There's our amplitude. There's a polarization tensor. But look at what happens to this factor. We're going to get a 1 minus 1 minus 2 pi IFL times that stuff. It's going to cancel. Right? In the denominator here, we're going to have a 1 plus omega hat dot p hat. And from this difference, we're going to get a 2 pi IFL times 1 plus omega hat dot p hat. Right? I just took this small L limit of the exponential. Can I have a thumbs up that I did it right? Thank you. Okay, so look, that factor cancels that one. And remember that the redshift was the time derivative of the time delay? It's probably written up here somewhere. There it is. So if I want to know what the time delay is when the pulse arrives, I just integrate the redshift. And look what happens when I integrate the redshift. Oh, I've left out my exponential. Gosh. I hope that's not missing anywhere else. I'm sorry, I left out the important e to the 2 pi IF tau. Okay, it's here, there, and I dropped it when I went down to here. Okay, so look at what happens. These factors cancel, and now if I integrate this with respect to tau, all I do is I bring down a 1 over 2 pi IF, which cancels that one. So look what I'm left with. So the timing delay as a function of tau in this short arm limit, that's the integral of z of tau d tau. It's just 1/2 p hat A, p hat B. There's going to be a remaining factor of L. And then there's going to be this integral, sum over A, integral df, integral d omega, HA of f omega, times the exponential factor, times the polarization tensor. But that is just the gravitational wave amplitude, HAB, at time tau at the Earth, which is more or less the formula that Matthias derived on the first lecture. If you want to know the response of a LIGO-like detector that has 2 arms, you know, this p hat here, there's the x arm and the y arm, and LIGO computes the difference So the LIGO response is proportional to the length, and it's just given by replacing here p hat A, p hat B by x hat A, x hat B minus y hat A, y hat B, where those are the two perpendicular arm directions. So in fact, this response function is perfectly general. It also applies to LIGO-like detectors and so on. And in fact, if you want to know how a LIGO-like detector responds when the gravitational wave frequency gets high enough that you have sort of order 1 wavelength trapped inside, then that expression will tell you the right answer. So, okay, I think if I look at the clock, yes, I'm going to interfere with lunch if I don't shut up. So, okay, are there any questions? I guess we can talk for one.
I have a quick one.
Yeah.
So this is also a plane wave, right? But if you have a wave packet, for example, and I wonder.
You know, it's a really good question. So if you go all the way back to our description up here, right, that's a description written in terms of plane waves. But in fact, that describes any sourceless solution to the wave equation, which is transverse and traceless. The plane wave decomposition, it's a helpful way of thinking about it. But it's not actually necessary. You could put in an amplitude, HA of f and omega, which describes an arbitrary solution, not one with plane waves arriving at you, but with circular wave fronts, or sums of circular wave fronts, or anything you want. So, and for example, the calculation going from this line to that line, I never use the fact that it's plane waves, ever. Because look at what HAB of tau and 0 is, right? Just plug in t equals tau and x equals 0 into that very top expression. It's the same thing I've got written here. So, in fact, this doesn't depend on having plane waves. The plane waves was important for me because, as I pointed out, that sort of intermediate expression, that this intermediate expression up here was kind of deceptive because it didn't really apply in general because it had this omega direction in it, and that was kind of hidden. Right? But the other expressions I have are completely general. So even though it's written in terms of plane waves, you could actually rewrite it in terms of spin weight 2 harmonics or other bases, and it would still be correct. You don't look very satisfied with my answer, so I might have missed the point of your question.
No, I just have to do this myself to believe it, but okay. Thanks.
Okay, my confidence has been shattered by the question earlier, so I think what I told you is right, but now I don't believe it. Okay, are there any other questions? Okay, we're going to continue tomorrow, and I'm actually going to now put some of this to application for PTAs and for how one analyzes the data. Thank you.